Thank you very much for coming back, for not running away. Apparently Ben ran away, but we'll see. So I'm continuing my story about cells, and what I want to do today is, well, monoids are kind of very special types of algebras. If you want to think of a monoid ring, right? And it would be a good question, at least some reasonable question. How does everything generalize for kind of general algebra, general finite direction algebra? So can you do some cell theory for those? Do you get some introduction theorem? And that's what I'm going to do today. The road is a little bit more bumpy than for monoids, just the monoid case is just really, really nice and smooth, but it's not so bad, so stay with me. So here's the reminder. That's what I actually want to do. Right? We have this picture of monoids and groups in the front, and the representations in the back, and the categorifications at the top of the slice. And what I want to do is I want to copy the theory of Greens and co. from the 40s, 50s, 60s of the last century, and I would like to see how it actually applies to whatever I would like to study, whether it's a category or an algebra or whatever actually works. Right? So as I said, today we will kind of take a kind of off track, a little bit different direction. So this talk is not strictly related to the last one on Thursday. So I'm not going to categorify this picture. I need to make sure clear, and we will see along the way why I don't want to categorify this picture. So the algebra, the general algebra picture. Well, I do want to categorify, but I can't. And you'll see why. And I would like to do some, well, we kind of discuss it in real time. So I was thinking about this problem for a while, trying to study those examples. So the good, the ugly, and the bad, which is certainly the wrong order, but that's just how they came up. And it turns out then, it took me a month to realize that this was actually all done in the 50s already. So, but anyway, we'll discover it in real time, and then we'll see the statements from the 50s, and you get a really smooth theory of, well, an introduction to a cell theory for algebra. Just now we have something linear, so it gets a bit more complicated. But it's always good to start with examples. So I would like to do the Brouwer algebra, or the Brouwer monoid. Let me now explain how that works in case you haven't done the exercises. So I would like to think of a certain number of points at the bottom, a certain number of points at the top. I think of the bottom as being the set one n, and I think of the top as being the set minus one minus n. And I would like to partition the union of those. I do it in the following way, that everything just has exactly two, so every part has exactly two elements. We try to copy the diagram from the bottom. Choice. So this is a partition, and if you would like to feed this into a machine, you would feed the partition into a machine. And it works as follows. So here, you see 1 is connected to minus 4, 2 is connected to 4, 3 is connected to minus 2, and the last one, which one was missing? This one, minus 1 is connected to minus 3, and that's a partition of the set. And each partition with two parts, with exactly two parts, gives you one of those diagrams. Okay? So there's the bottom one. If I haven't messed up, 1 should be connected to 2, 3 should be connected to 4, and the top is connected minus 1, minus 3, minus 2, minus 4. And this is a, well, and then you get the usual picture here by just stacking them on top of each other, composing diagrams. And we get one example. Like this. This thing. Yeah, it looks good. So it simplifies. It just doesn't matter what I call it. It's a partition. So this point is connected to this point, no matter what's in the middle. There's this picture upstairs. And upstairs with the campus. Right. And we get this monoid out of it. This was the Brouwer monoid. Was one of the first of its kind of this diagram type. monoids. It goes back to Brouwer in the 30s of the last century in their study of invariance of symplectic orthogonal groups. But we don't need to know that. It's just a combinatorial picture. And I would like to discuss now the Brouwer algebra, which was actually what Brouwer studied. Brouwer didn't study the Brouwer monoid. The idea is, whenever I have an internal component in this partition picture, it doesn't change the partition, so I just take it out. And now I just decide, if I have, can I copy the picture? Oh, let's forget it. Let me draw a new picture. If I have some internal component, something like this is a very boring picture, but anyway. And under composition, I find some internal component. What I would do in the monoid, I just ignore it because it doesn't change the partition. But in the algebra, what Brouwer tells us is to just evaluate those guys to your favorite number, your favorite element. So we call delta for the Brouwer. Some fixed field, it doesn't matter. And this one is delta. Say let me simplify the diagram. Yeah, I can do that actually. Oh, it was actually this one already. It's great. And you get a delta squared. That is internal component. Color now, thanks to topology. Color now, so here's one component, another. Each one is a delta. Delta squared here. Same, otherwise exactly the same picture. And you get what is called the Brouwer algebra. Here in my, well, I don't have purple, but here in my picture, there's this purple circle in the middle. I get rid of it, and otherwise you just look at the partition you see and simplify the picture accordingly. So Brouwer introduced this, and representations of this algebra are related to orthogonal and symplectic groups. And it looks very much like we did yesterday. It's a bit more complicated maybe, or easier, depends on your taste, than the transformation monoid, but it looks very, very similar, part of the same type of diagrams. So what I would like to do is, obviously, I would like to write down the same statement again. There's a slight problem that it doesn't quite fit. It's not a monoid, so I have this kind of linear parameter here around. So I pull out, give me some scalar. In monoid I can't do that, so that's not a monoid. So I just can't apply H reduction. But, well, you see, my favorite strategy in life is always just to ignore problems until you can't anymore. So we just go for it, and we just pretend we can do it and see what comes out. And it turns out that this is a good example, right? So it will work. So, and that's a good reason for it, which I'm going to explain later. Right? Let me say it again. This is not a monoid. I can't apply the theorem, but I still will apply the theorem. I completely ignore that I can't. Okay. So what are we supposed to do? We're supposed to write down idempotents. We're supposed to write down cells. We'll do that in a second. And we are supposed to then kind of classify everything according to the theorem upstairs. And the only thing that changes here already, so I will kind of change the setup as we go, right? So strategy, ignore problems until you can't anymore, so I change the setup as we go. Is the correct notion here, it's not that one of an idempotent anymore, but the one of a pseudo-idempotent. So here's my example. Let me explain why. So my delta is some parameter from some field, very good. And a picture like this, stacking on top of itself. This is almost an idempotent. You see, we're going to go forward. Also scale up. It's an idempotent. So scale up, so I can just get rid of it. Think of my picture. Now, if you scale, just do the one where that's in front. That just goes to work. It's not zero. To the field. In this guy squared, what will it do? Well, it's going to spit out the delta. Yes. So the eigendelta, just get rid of the eigendelta. That's what I'm doing. And spit out the delta, we get the same picture. This guy squares. And now it will simplify to one of the delta. So this is nice. Trick you can play, very simple of course. A trick you can play in the linear world. And it turns out that this is the correct notion because I can always rescale everything. So we should look for pseudo-idempotents. These guys are called pseudo-idempotents instead of idempotents. Because that's what we learned from Brilliant Code. That's the first difference. The only difference right now is that I'm looking for pseudo-idempotents and not for idempotents. And I just go for it. So let us discover the Brouwer algebra cells using exactly the same definition as before, no change right now. So what can I do for the Brouwer algebra? Well, the picture goes as follows. Draw a diagram at the bottom by just pushing all cups downstairs. This I push all cups back down. Caps, I push all caps down, thank you very much. And I push all cups up. I push all cups up. And you can always do that. Just push everything, it just depends on the partition itself. And whatever ends in the middle, and this is now a really bad picture because nothing ends in the middle. Just reconnect. Whatever is in the middle, picture here, will be just first strands again, very similar to transformation monoid, and they can be removed. So what ends in the middle is symmetrical in number of first strands. What ends at the bottom to those cup diagrams, ring diagrams with strands. Sorry?
If you draw some strands, that'll be
Oh,
in your trapezoid.
Oh. I'm not sure. Never. Alright, I should draw something. Very good. Anyway, the point is now, this is my picture, and now it's very silly. I should have drawn them on the side. Or someone don't. Because now I don't remember which one's left and which one's right. Like I mentioned. But if I stack something on the top, nothing at the bottom will change. If I stack something on the bottom, nothing on the top will change. In the middle will never change. Which just means the picture we had last time, right? The relations here, y equals z times x for the left one, y equals x times z for the right one, y equals z x prime for the two side of the look. I can just read off the steps. So let me just pretend this is a correct picture here. Then if you follow a row, then the top diagram is fixed. If I follow the top row, I always see this picture. If I follow a column, that's exactly the reason that you don't change. On the stacking, if I follow the column, then the bottom picture should be fixed. So first column would be this picture. And in the middle, I always see the same number of first strands, and it just permutes. So what I get is that the Brouwer algebra, cells again indexed by first strands, so it's again in linear order. Nice linear order. Where you have an S n here. Well, I can only couple away things, so I go from some 2, S minus 2 here, n minus 3 here, Sn minus 4, up to, depending on parity, S0 or S1, which are kind of the same groups anyway. But up to parity, I see either one strand in the middle, or I go down to pictures with no strands in the middle. And as before, I just color the idempotent cells here for the bottom one, which is just a symmetric group itself. Clearly, the identity is a pseudo-idempotent, and for the other ones, I will hit the picture on the board. With this guy here, is eigenvalue delta, so as long as delta is equal to 0, that's my pseudo-idempotent. So here's my picture, which indicates that the Brouwer algebra in this case should have 3 simples, let's work over complex numbers, 3 simples for the bottom and 1 simple for the top. Right?
Who's confused out of curiosity? Please interrupt. If you're confused, you should be bothering because this is for you. Are people happy? I see some unhappy faces. Interrupt.
Yeah.
I already know everything, so.
Oh, that's great.
Anyone? Everyone's happy? Okay. Never mind. My bad.
Maybe you're unhappy if you're going to ask a question.
I was unhappy. I just wanted to try to emphasize again the point he's trying to make about the left cells and the right cells and the shirts and the pants.
What?
So each one of these diagrams you should think of as wearing an outfit, a shirt and a belt and and pants. A pair of pants. And the shirt you drew, can you draw the shirt of the upper left diagram?
Upper left diagram.
Yeah.
Upper left.
Let's start with the upper left diagram on the top. There is the shirt. And could you draw the pants?
I can draw the pants. In there.
Good. And can you draw the belt?
Sure.
Perfect. Okay. So every diagram has a shirt and pants and a belt. And the point is that if you now you're going to ask what happens when you take this diagram and you stack another diagram on top. Okay? The claim is that this can completely change what shirt you're wearing. And it can produce scalars, because maybe you make a circle out of that top. But it will never change the pants. Okay? And so it's like a doll where you can mix and match shirts and pants, but if you left multiplication will only change your shirt, right multiplication will only change your pants. And you can indeed change the belt as well. So left multiplication changes the shirt and the belt. Bottom multiplication changes the pants and the belt.
But not the number of strands.
But not the number of strands in the belt. It could change the number of strands in the belt.
Oh,
It can bring you to a lower cell.
Yeah.
It can never increase the number of strands in the belt, but it can decrease the number of strands. So let's take the diagram at the bottom, like the upper right corner of J3.
Maybe there's a very simple way. Let's take this there.
Let's take the upper right diagram.
Upper right diagram. The crossing one.
The crossing one. That's right. So what's the shirt? The shirt is the identity map. And the pants are the identity map. And the belt is the element of this group in the middle. Okay?
And just pull this straight. That's totally good, yeah.
Okay. And when you act by some diagram on top, it can, like a permutation, it'll make its way to the belt. And if you act by a cup on top, like a cap, it will bring you to a lower cell. Or higher cell, higher cell. So if you ignore things that bring you to higher cells, then all you're ever going to do is change the shirt and the belt. If you go to a higher cell, you're in a completely different kind of outfit world. And so you can change the pants because the pants are completely different kinds of pants. Like three-legged pants and one-legged pants.
So we could say that the group-like elements are the naked ones.
The group-like elements are wearing a belt, which is good enough.
Good enough. Only a belt.
Okay. Thank you. Sorry.
No, there's a great amount of belts and shirts. I hope the picture now makes some sense. Well, certainly it makes some sense to you, but right. And the difference really is that if delta is 0, then I might have different pseudo-idempotents. So this picture is not pseudo-idempotent anymore for delta equals 0 because second itself. Example, delta is 0. Very different from the monoid case. In the monoid case, I just divide idempotents. And now it kind of depends on my precise setup. In this case, I'm kind of lucky, and I still have pseudo-idempotents in the middle. Let me just do another example. Itself. Put it straight in the middle. Same picture again. So I'm lucky. It doesn't really change any classification here. Still same classification. But in general, I could be unlucky here. Think of general setup. I could be unlucky in.
When these pseudo-idempotent cells are colored, I don't see any specific color around idempotents. What do you mean by colored?
Everything that's purple.
Everything is purple in the blue purplish in the background.
Oh, I see.
Okay. So on top, everything is a pseudo-idempotent. Every cell has a pseudo-idempotent in the bottom. There was diagonal ones.
The bottom is one cell. So
Yes.
that's just one purple containing 6 elements.
It's the same notation from yesterday. Yeah? Left cells, right cells, J cells. Going upwards.
But the white cell is also idempotent.
The white cell.
Why are they
Not if
white?
delta is 0. Not if delta is 0.
Not delta is here.
Oh, it's good? Okay. Yeah, makes some sense. And the idea actually goes back to this paper from the 1990s. Really built. Highly recommended. And what we just discovered, basically, Ben explained it very nicely, is that my two-sided cells correspond to through strands, to the belts. And it's not hard to see, it's not completely obvious, but it's not hard to see that all cells will have pseudo-idempotence, unless you hit the delta equals 0 case. So there's one extra case, so that's why I have A and B here. It's a little bit sad that there's some kind of parity nonsense that turns out here. If I have no strands in the middle, which might happen for A and B, I guess, I stack any picture, stack it on itself. By construction, I always get circles in the middle. All of them are 0. Yeah.
You didn't put that on itself, but that's okay.
It's not stacked on itself, yes. I can also stack it on itself. So now I have an A and B, that is different from the monoid case. So still the symmetric groups sit inside, they play the role of the EH from before, but there is one difference between this parity, and there's one extra case, it's the top cell, which is the one with no through strands, just don't produce any simple module, and otherwise you have the simple modules. That's what you see again. I'll just X, Y. I guess in 2, 4 partitions of n, partitions of n minus 2, partitions of n minus 2. And that's the classification of simple modules for the Bauer algebra using the H reduction, which we can't do actually, as I said, but it still works. So this is the correct answer in this case, which is kind of a little bit amazing. And certainly we're up for something if you see a theorem which is not supposed to work and it still kind of works, then you know that something is going on. Okay. Let me discuss some of the others. So they're all very simple actually. They're all right as partition algebra, simple drawing. Ben, what's your favorite picture?
For which one?
Northeast or whatever?
I'm confused. Robert.
Okay. Right. Fantastic. So they correspond to position. You were confused because you weren't here when I was naming the positions. Okay. Let me re-explain again. They correspond to positions. So the bottom have 1, 2, 3, 4, 5, 6. Set 1 up to n, 6. The top I have to set minus 1 up to minus n. The partition you see is just you see the 1 is connected to minus 2. 2 is itself. 3 and 4. 5 is itself. 6 and minus 5. Minus 1. Minus 3. And minus 6. Minus 4. And it. Partition of the union of those sets. And all of these diagrams are partitions of union of sets. And you can just form some algebras from all of them. The symmetric group, for example, is just a very simple one. You're just allowed to choose element sets of all 2 parts for the 2, and you're only allowed to go back to bottom and top, and so on. root bra algebra, it's just the name, is the one here. It's given by parts of size most 2, right? Parts of size 2, but also parts of size 1. The planar symmetric group is just trivial. So the right hand side is just really the diagonal monoid as a partition monoid, and on the left hand side you just take the planar version of those. Okay? So on the left hand side I'm not allowed to cross. If I'm not allowed to cross in the symmetric group, I get a rather trivial group. The planar symmetric group, which is just a group. If I'm not allowed to cross in those diagrams, I get what's called MO. And for all of these, you can just repeat what we have said, because Ben's picture works absolutely well. You still have a shirt and a belt. You just pull everything, let's say this picture, pull in this case, all of these elements downstairs. I still have something in the middle, like belt here, pants here, and I have some stuff at the top. So I got the right number of strands. And you get the same type of cells, they're now again ordered by through strands. Left cells have a fixed bottom, right cells have a fixed top, all that you know. And what ends up in the middle is always a symmetric group in this case. That's what you can do, permute, so you get exactly the same classification. Again, you need to be a bit careful if you want to do the delta version, because now components get stuck with one. It's kind of really the same. Yes?
Sorry, I wasn't here. Yesterday you talked about the strand thing. So the transformation monoid, what is like this? What is a rule? Or like if you have like two things going to the same thing, like what's the?
In the transformation monoid, those guys will be the pants. These fun things. For sure, in the middle. Can you see it?
Sorry?
Can you see it?
Yeah. So you squeeze as many things as you can into the pants and shirts, and what's left over is the belt.
Basically, yes. I squeeze them right just to the bottom. I squeeze those things to the top.
Okay, I see. Thank you.
And maybe this is confusing a little bit. So that's what duality. So the top and the bottom will just look different. While all of these pictures are dual to one another. So caps at the bottom and caps at the top. This has a linear order. This has a linear order. All of these have linear order. Just in the number of the belt, the through splits.
So the belt will always be part SM.
And middle is always the same. Or S lambda in the number of through splits.
For the ones on the right side, the ones on the left are not allowed
Good
to
point.
cross it. Yeah, so their belts are just identities. Okay.
Yes. So in the planar version, you just write it down in planar and that's because the right column the symmetric ones. The symmetric ones, the H's, will always be some symmetric groups in the number of through strands. They're not SA because H is my number of points so blah blah. And here the H is always trivial. So maybe I'll just classify, let's say for you, simple representation of this one, but just from the pictures. Let's do it why not. I'm not allowed to cross anything, so this is a pants picture. I'm not allowed to do this. I'm not allowed to cross anything, so this is a shirt picture. Since I'm not allowed to cross anything, the trivial will end in the middle. Planar symmetric, right? So this is always what you see in the middle. Again, otherwise, the smooth strands classification is the following. The C first penetration, PSN in the middle, PS2 in the middle. Again, this is my cutting off. Less 4. The planar symmetric group is not very exciting. It has one simple representation. So you get one simple per JSON. Unless you are in the top case, then you kind of depends again delta is 0 for those diagonals.
For like Robert, you still do a delta when you just have 2 points that come together and get deleted in the middle.
Yeah, if you have a barbell.
Yeah.
Of two dots connected by a line. Yeah, that's delta.
Okay. It's still a connected complex. Okay.
Yes. Makes some sense.
Yes.
Right. But this is what you see in the middle. And then you get classification by the symbols of those events. That's it. Just according to the number of strengths. And you can really do all of them if you want. Works over any field, completely in general. Okay.
Sure.
Yeah.
Does it still work if we put one parameter for barbell and not one for
Oh, that's a good question. You can for some of them say, let's say this is the one eta, and every circle is a delta. You get 2 parameters, no change. You get a slight difference. Now you have to check kind of what the pseudo-idempotents are, because it changes now depending on the parameter. But otherwise, it's exactly the same picture. This is really, really powerful idea. Works in any setup you want, in some sense.
Then, would you mind writing on the a bit more?
Yes. So, I can evaluate barbells. Parameter that's called eta for some reason. The circles delta. And I will see what change. This is better. So roughly here maybe. Okay.
And you write very light, so you should always write in color. It's a lot easier to do.
It's not my job. But I can. Right. Any other questions about this picture?
So then if you have like you have it perfectly done. This BR underneath a robber, right? You have this strand that's going to a barbell that just turns into a barbell.
No, that's 2 different alphabets.
No, I know, but they're.
ER has no barbell.
So which one are you thinking about now?
So you can still have a strand to a barbell,
Yes.
and that just comes down to the thing across. So
What? We want you to draw a crossing with a dot on top. Draw the way.
Well, it only counts as a partition. So, and partition is the same as.
that's just a single thing. Okay.
Yeah. So I'm not writing down relations for this. It's a bit tricky. It's not really hard, but it's a bit annoying because if just all the relations, so it forces partition to be the same.
Sure. Right. Yeah. No. Sure.
Any other question? Okay. So the upshot is here. For all of these, although we are not allowed to do it, H reduction works perfectly well, classifies all simple representation, and you can beef it up. You can compute dimensions of symbols or something. But we're not doing that right now. We're just classifying simple representations. Okay. So let me do the ugly, which still works, but it's much more complicated. So I would like to think about the symmetric group. And I would like to apply cell theory to the symmetric group. Which sounds very ridiculous because I told you yesterday it's a group. So cell theory is pretty boring. But I will kind of use the linearity here. I will choose a different basis and do exactly the same. And I get a cell theory picture for the symmetric group. So I can also do the symmetric group. From this picture it looks like these are kind of the group type objects are kind of the building blocks. And there were just H cells for all of them. And now I'm trying to, well, here's no splitting, this is one. And I'm trying to split this into a finer picture. So we get, again, the partition classification of the symmetric group. And the symmetric group here, you can think of it as the symmetry groups of simplices. We'll see another symmetry group in a second. Well, not in a second, in a while. This will be the bat. So not all groups work in this way. Just the symmetric group is very, very, very special. That's not a very surprising statement. I'm just trying to do it here. Of course, I know the representation theory of the symmetric group. It's no big surprise. But maybe we can do a little bit better than Frobenius. It's very amazing. And we can. Let me try to explain that. Okay. So what I list here are the character tables. So let me see whether we understand how to read this. So the characters are down the first column. There are 4, there are 5 characters, which Magma likes to call x1 up to x whatever, x5 in this case. And along the rows, for rows, you will see the conjugacy clauses, and the usual character table is the square and the conjugacy clause and the characters. Ignore the middle slides for now. That's kind of the characteristic nonsense that comes in here. And these are the characters, of S5. We kind of would like to obtain them, those simple characters, in a different way. And the idea how to do this goes back to this famous paper of Kasher and Lustig. It was later worked out by Lustig. And it's this J-reduction approach. And J-reduction was just a statement that for each J you have a certain number of, so for each two-sided cell you have a certain number of associated simple points. And it turns out that this kind of works in general, I will comment on that later. But it turns out that Lustig's approach here actually also gives an H reduction in this case, which is very, very rare and usually don't happen. Okay? That's what I'm trying to do, and let's try to see actually how that works. I need to modify the notion of a cell now, right? As I want to go along in my attempt to kind of use H reduction in general, I kind of modify everything. In the previous case, I was kind of fine, but now we'll hit the problem that I'm linear. So what I'm doing is the following. It looks very similar. As you can see, it's almost the same as before, but there's a slight difference. I use this funny symbol with a just use color. Subset is a plus. And this means the following. So what I do here is very, very strange. But I can do it now because I didn't do it well. So I choose a basis, B, and there are some elements x, y, z, whatever. Okay. Choose the basis, very important. Choose the basis. And I define my cellular with respect to the basis exactly in the same way as before. So y is left lower than x. Those are base elements. If I can find z, correct now, such that y appears in the expression of z times x, if you look at it.
That's x lower than y, right?
Sorry?
X lower than y.
That's x lower than y. What? And really the same idea, just in linear. So these are all basis elements. Everything used to be the basis element. You can express this in terms of basis elements. Subscalar e1 times whatever x will be just called x1 is squared. b2 times x2 and so on. And whenever you see a non-zero scalar here in front, then it is always.
Could you explain that better?
Sorry?
Could you explain that better?
Yes. Alright. So let's say z times x is equal to b1 times x1, or 5 times x1, 4 times x2, plus 3 times x2. Okay? And let's say at 0 times the rest. Then I would have x1, x2, and x3 are all bigger. And all the others are.
numbers like linearized things, so you could have scalars in front of the thing.
We can have scalars in front.
So in this case, would like 100x1 still be like subset plus 5x1 plus 4x2 plus 3x2?
No. I only take basis elements. Huh? No scaling, no sums of basis elements, only basis elements.
We're putting a partial order on basis, a pre-order
On basis elements.
Oh, okay.
I end up in the middle. I need in the middle. I need linear combinations. And on basis elements, think of the monoid example. For the monoid example, I had a kind of natural basis, the monoid basis, and I did exactly the same. Just that you don't have direct sums because element times element is element.
I see.
Make some sense?
Okay, yeah, I see.
Sorry, I just want to
Yeah.
understand. So like something is subset plus or something if it appears as a term in a linear combination with like non-linear coefficients.
Yeah.
Yeah, a basis element is subset plus of an arbitrary element if it has non-zero coefficients.
Wait,
Yeah. Sorry.
does the C here have to be in the basis or here?
The Z in my notation is also in the basis.
It doesn't matter.
It doesn't matter because you can take linear combination, but let's say it's in the basis. Make some sense? And I would like to play exactly the same game. Right? Left cells, right cells, J cells, H cells, intersections, and measure now how far you're away from the group-like elements. That's what I said. So, for the case from yesterday, for a monoid, for let's say for the group algebra monoid, some field, monoid. My choice from yesterday was the monoid basis, and this specializes to the case from yesterday. The exactly green cells in the sense from yesterday for this special case. But now I'm allowed to vary my basis. I could choose for my monoid, I could choose a very different basis, and I will get very different cells. We'll see an example with a symmetric group. I choose a different basis, I don't choose the group element basis, and I get interesting cells. For the group element basis, I get boring cells. That's a new power. It's a little bit annoying because I need to write down this relation, but now I have the freedom to choose the basis. Kind of what you should think of that again, the invertible elements end in the bottom cell. But it's not quite true because I might not have any invertible element in my chosen basis. It really depends on the basis. Kind of all the invertible elements stick in the bottom cell. For the very same reason. I can always turn that around. In this case, my basis was the diagram basis. The diagram that you see. And my linear cells, I call those guys linear cells, were exactly the cells we discussed before. I could again choose a very different basis. It doesn't make any sense to choose a very different basis here, but I could, and I would get a very different picture. To make some sense. And it turns out that you can actually choose a basis for those guys. And I need to explain a little bit more before we do go there. Let me draw a picture for you. I think I have one on the next slide, and then we'll go back to this one here. So we have now this notion of cells, all it depends on the basis, some picture like this. Yeah? I have some idempotent somewhere. What I can do now is because the relation, think about the relation. The multiplication, by definition, always gets you up in the basis. Right? That was the relation. I have x to the 1 to y. Let's try dollar again. Whenever I can find y in the expression z times x, so whenever I multiply, I always go upwards. Or I can stay where I am, but I never go down. If you particular, again, I think a nice filtration from this algebra, given by just going upwards, and I can just kill everything, fix one of them, and I kill everything above. And I get a new algebra, which I call SJ. J is the two-sided piece. Killing.
You want to make a good clarification?
Sure, go ahead.
So, when you're talking about quotients of rings, you want to take a quotient by an ideal, and if you take a quotient by a two-sided ideal, you get a ring. But suppose you restrict yourself to only consider ideals that are spanned by elements in your chosen basis. So you choose a subset of the basis, you take its span, and you pray that it's an ideal. It's usually not an ideal. But suppose you're only allowed to consider spans of basis elements. Well, exactly this condition, this definition, says that if you take x and you take everything lower than x, that this will span a left ideal. Bigger than x, sorry, that this will span a left ideal. And similarly, if you take everything bigger than x on the right order, you get a right ideal. If you take two-sided, you get a two-sided ideal. So if you're interested in two-sided ideals spanned by basis elements, you have to take like everything in a J cell and everything higher than it. And that will give you a two-sided ideal that you can take the quotient by to get another ring.
Exactly, so I have the order to play around with. That's basically what Ben said. And that's why at the top, the green one is 90. And the conditions on the edges, the intersection left and right sides, actually force that this is also somehow. So there's also the SH. SJ, and now an SH.
So SJ is the ring you get by killing all higher cells? And but are you just only looking at the span of things in the
I
cell?
only look at the span here.
So it's a non-identity.
It's usually a non-identity ring.
Okay.
I comment on that in a second.
Okay.
The pseudo-idempotencies make them unital. In general, it's the same nonsense as yesterday. I should work with semi-groups, not with monoids. I kind of like unital things. I kind of have to do some choice here. And if I have pseudo-idempotent, the pseudo-idempotent will unital. So I really only it doesn't really make a difference again, but in this, let's just say I only consider really the red box. Again, the order forces that this is the red and the green is also an ideal. So if I kill the red and the green, I take the red and the green and I kill the green, I get an ideal, which is kind of an algebra, but it happens to be the pseudo-idempotent makes it actually an algebra. Yeah, and that's exactly kind of what I did before. If you think about the diagram picture, this was just very simple in this case. It's a symmetric group. But in general, you can end up with any algebra, basically. Make some sense? Everyone happy? Yeah, so that's the main change now. I have those linear orders with a chosen basis. And I get algebras instead of groups. Okay, but in principle, I can still ask for the same. Do I get a classification by just looking at those guys and simple representations of those little algebras, which is still a huge reduction, right? You still, in general, have those ridiculous pictures, and you can still get a huge reduction. Okay, and it turns out that you can, for the symmetric group, there's a basis which I'm not going to explain right now. We can talk about it in the exercises, which is called the Lustig basis. Let me just explain my notation here. And it's really adapted to the cell. It gets you some nice cells, and I can explain the cells in a second. First, let me explain the notation. I think about the symmetric group is generated by the reflections at transposition, I guess. So my Sn generated by 1, 2. This is a 1. Let me try that way. 2, 3, 3, 4, and so on. And just super lazy. Because I want to get everything on the computer, I just call this element 1. Just I call it just elements by the new number of C. I just call this element 2. Right. And then symmetric group now has those guys, for example, S3 would be generated by 1, 2, and the relations between 1, 1 is trivial. We can draw this work notation as an empty set. 2, 2 is trivial. We can draw this work notation as an empty set. And 2, 2 would be this twice. And then you have this break type relation. Right. We can also write down the elements of this symmetric group if we want. With a unit in this work notation, empty. We have 1, 2, 1, 2, 2, 1, and 1 to 1, which is the same as 1, 2. And categorifications say now, I'm not going to read the details how to do this, but categorifications say now that there is a basis, which has this indexing set, which is called nt 1, 2, 1, 2, and so on. Right. There's a different basis. I'm not choosing the usual basis. I'm choosing a very different basis. And I get those cell vectors, which I will explain in a second. Let me just explain this case. In this case, we have this forward picture. So that's S3. I just wrote down the 6 elements for you. Generally, we have n factorial elements, so don't think we write down as S5. S. And S has to be like this. Same pictures as before, linear cells, left cells, right cells, two-sided cells. In order to verify this, I would need to tell you the multiplication table of those base elements, but I do want to get such. So you can try this. And I just call it W0, which is one goes in this direction, 3 cells, this direction. And I will tell you the indexing for the cells in a second. But that's roughly the pictures you get. Okay? So there's a mathematical basis, categorific basis. All you need to know is the multiplication table. I'm going to tell you the multiplication table, what I actually do on the exercise sheets. And you can just verify that, right? The multiplication table is what you need to know in order to check what the multiplication of those elements is. Okay? And it turns out that in this case, well, let me just show you the statement. Okay. It turns out that in this case, the statement of Cassel and Lustig is that there exists a basis such that A, B, C hold. Okay? The first statement is everything has a unique apex. It's actually order simple. Again, this is non-trivial statement. You can again order symbols by apex, so like a two-sided cell. Everyone spits out a certain number of simple modules. And I can tell you exactly how many, because they also say that let's work with complex numbers. Let's work with complex numbers. All the SHs, all those little boxes there, are just the ground field. That's get simple modules for the ground field. It's not really hard. That's one. So one simple module per cell. So we better hope that, let's say we're working with complex numbers, that those J cells, the two-sided ones, are indexed by positions of n in detail. So they also show up. So these guys are indexed by positions of n. So something like depending on the locations. I think I use this one in a second. So this is 1, 1, 1, partition 1, 1, 1. This is partition 2, 1. This is partition 3. in general, for any essay. We have this picture, everything orders by partition. And that's of course the classification we want, right? So we get a classification because every J cells contain one simple module. It's just the ground field. We get one simple module per partition, which is exactly the classification we want there. And now it's kind of a final statement, just directly from this approach of this asymmetry. And this again was in general by any field, just get a slightly different statement because your pseudo idempotencies are different. Let me just show you a picture again. So if you do it over characteristic 2, if you're very brave and want to do characteristic 2, this is how the cells now look like. So you get different pseudo idempotencies. Again, basically what happens is that you get pseudo idempotents, they spit out a scalar, but the scalar might be 0 in your field, and then you get those non-pseudo idempotents, the near-important elements.
So you're saying it makes sense to think about modular representation theory as a group in terms of the usual monoid cases?
Yes. Alright, let me be completely explicit and match. So, by the way, this just says the J reduction works. So, the existence of an apex, that's what Lustig shows, that works. Let's call it the J reduction, so I can reduce to the APC. And this works in this case, and even the H reduction works. That's what Lustig showed as well. Okay? And just for the record, to come back to your question, you can make this work over any field. You get P restricted partitions, whatever. Okay, let me do the example for you, just to match it with my character table. Character table, Magma tells me there are 3 representations in characteristic 0 over the complex numbers, and I give 3 partitions, which is exactly what I want. And I get this really good, beautiful correspondence between exactly what I wrote down there, between the partitions and the simple representations. Works for any symmetric group. Okay. Oh, yeah.
Are these objects meant to be shaded, or do the shadings mean something different?
What the diagonals are shaded. So what is the question?
Off diagonals.
Oh, the off diagonals.
B1 and 2 should not be shaded, is that correct?
I need to. Oh, good point. I actually forgot to say that. No, they're supposed to be shaded. They are pseudo idempotents in SJ. That's what I'm looking at, because they kill higher cells. Let me write down the formula. That's a good question. Let me write down the formula. Ben is my expert on this. Correct me if I'm wrong. B12 times B12 is B12 plus B12
Times 1.
and somewhere it's equal to.
No, B1 to 1.
Oh, this one. But I don't care because this sits in the bigger cell. Locally, it's all I'm caring about because I always reduce the expressions. That's a good point. Yes.
So can you say something about like if I once I pick like for example like a trivial representation in like the 2-1 partition, like how do you reconstruct the representation of S using that?
Sorry, what is the question?
Like how like
Same procedure. Very good question. Same procedure as before. You induce it and look for the head of the module.
sorry?
You induce it. Same procedure as last
We
time.
never really discussed the procedure for taking representations of an essay.
I never did. Maybe I did use the exercise, but you induce a representation because now you have a subalgebra given by those SHs. And those SHs spit you out the trivial representation you're looking for, and you reduce it to the whole algebra and look for the hat of that module.
Hat.
The maximal maximal subversion.
Okay.
That's how it's simple.
That was the circle.
The simple.
The hat, the maximal submodule.
And then
Okay, so you get a representation of the procedure, just a reduction.
A lot of people really seem to want to know this after the last exercise. So maybe after you're done, I'll do a little bit in the exercise session.
All right, you can discuss it in the exercise session. I'm running badly on time anyway, I guess.
Yeah.
There's a very explicit procedure. But right now I'm just discussing the classification. So again, if you want to know more, you need to work more. I'm just interested in a parameterization of those sets.
Sorry, stupid question. So first, every element is pseudo-input one higher.
That's probably wrong.
In characters is 0.
Like, but in this example it is, right?
It is example it is, yeah.
I think because the intersection of every left cell and right cell is one element.
That's right.
I think, isn't it true that every
It's absolutely false.
Yeah.
BST,
Still jump off.
depends on what my BST is purely hypothetical.
No, I mean it's pseudo-input one times.
I guess the scalar
Because
is
it's
0.
always 0.
Okay, all right.
It could be 0.
Right, but it's pseudo. It's not such a pseudo. Right.
So it's either nil voids or pseudo hypothesis.
Yes.
Okay.
And
Yes, that's a fact.
Okay.
That's something.
for example, over in characteristic 2, the top one will be the input set ones with the rest. So are the middle and the diagonal elements. So the shading of my picture depends on the ground field. The overall picture doesn't depend on the ground field at all.
Let me make this different clear. If you have an element in left cell L and right cell R, and you square it, because the left cell L gives you a left ideal, and you're multiplying it on the left by itself, it's going to stay in that left cell. So it's going to be in that same left cell. It's also going to be in the same right cell. This is all modulo lower terms. So whatever you get is going to stay in the same H cell, guaranteed modulo higher cell. If your H cell is one-dimensional, then you're going to get a scalar multiple of itself, but that might be.
Is there a formula for this condition? Yeah, sorry.
All right. Oops. And the classification still works. So if you look at this table, it actually tells you the bad primes and the characters. Sorry, but it tells you that the polygating velocity is equal to 2, and that's really bad in characteristic 2. So what you need to do in characteristic 2, I just tell you the answer, it's called Brouwer characters. You just cross out, in this case, the bad row column, and you have remaining characters, those who like now, the trivial representation, the sign representation are the same in characteristic 2. And this one states what it is. So we have two representations in characteristic 2, and well, we have two pseudo-idempotent cells, so it's still a perfect match. You can characterize which cells are pseudo-idempotent. This is this notion of p-restricted partitions. That makes some sense. Works for any symmetric group. You can write this down completely explicitly. Any characteristic. That's again an introduction. Any questions? Yes?
And so I'm sorry if you already said this, but and it's a fact that over any characteristic you always sort of have enough pseudo-hypotheses.
Yes. It's part of the ABC theorem upstairs.
Yeah.
You want me to speed up?
I'm trying to do this.
I can easily speed up.
Please.
So I'm running late, so I'm cutting away something from my own exercise session. Is that so far? All right. This is great, right? This is absolutely great. It's again the same as for the diagonal algebra. It's just very different, and it still works. It's pretty cool. Same as for the monoids. Very different. It still works. It's pretty cool. Okay. Symmetric group. I think we're very happy at this point. Maybe we should stop, but it will get a little bit disappointing now. So it doesn't work in general. And I'll show you an example of how it doesn't work, where it doesn't work. It looks very similar. So it's a dihedral group, which is the symmetry group of the N1. So D4 is a symmetry group of the square, which I draw in this notation. So right. It looks very, very similar, just has a slightly different operation. And everything goes wrong. So my dihedral group, N, again, I just write 1 and 2. Super lazy. I just draw my 2, and use the word rotation. Same presentation, 1, 1, 2, 2. These are the two reflections that you can see here. The blue one and the red one, which is reflection square. Reflection square identity. And then you have this funny, very long type break relation. So n symbols alternating 1, 2, 1, 2, 1, 2 is the same as 2, 1, 2, 1 n symbols alternating. And you could try to visualize that if you want. I tried to. So if you reflect here, and so if you reflect, then I'll skip it. I skip it. You want me to skip it? Very good. It works. And again, the representation theory is well understood, and I would like to play the same game. Very good. You can look at the character tables, they're not integral anymore. And what Lustig showed is the following. So you use the same order, so no change really. I'm much faster than before, but there's no change to this point. The same slide as before. You use the same order, you use the same basis, just for the Hilo group, and try to play the same game. Okay, again, I'm saying here I fixed my basis, which is a Lustig basis. Okay, I'm doing exactly the same, right? No change. Same slide as before. No change. And I write down the cells, and that's how they look like. So in general, just down. There is again a parity nonsense. What? Basically, all it looks like is very similar to this graph. There's Bm to the bottom, with the longest one, which is this one here, top. And then we have those blocks of elements. So V1, V1, 2, 1, V1, 2, 1, 2, 1, and so on. Let me just write 1, 1, 2, 1, 1, 2, 1, 2, 1, so on. Depending on n, right? By stop at one point. Here we have 2, 1, 2, 1, 2, 2, 1, 2, 1, 2, so on. And 1. Okay. And the remaining ones is assembled into off diagonals. 1, 2, 1, 2, 1, 2, so on. 2, 1, 2, 1, 2, 1, and so on. It's much bigger, right? Before we had everything was just on size 1, and now it depends on n. It's going to be arbitrary. And it turns out that there's an even odd edge here. So let's just look at the examples here. The first one is D4, that's even case. The second one is D5, that's odd case. Just to be sure we are on the same page, D4 has 8 elements, so I count 8 basis elements, I hope. D5 has 10 elements, so I count 10 elements. And they arrange themselves in the following pattern. Let me write it down in the simplified way for you. I just record now the number of elements. One element. Here is a little bit annoying. So for D4, let's say 2 elements, 1 element, 1 element. That's what it is. For D5, and now I'm missing my reps. Green is D4, red is D5. I get 2 elements here. 2 elements everywhere. As a 2 by 2 draw. Okay, and now we are kind of in trouble. Because it turns out that all of them contain 2 line elements. It's really this picture with the coloring. But you do the calculation, and in the bottom case, what you get is the SH is a bit more complicated than before. Z mod 2, but in the top case, it can't quite decide what it wants to be. When it has 1 element, it's C. When it has 2 elements, it's Z mod 2. And they have a different classification of simple modules. So what is my age reduction regime? Okay. So I have different ages now. That's very different from the monoid case. I have different ages now. And that's something I don't like. And this actually makes everything wrong. So Lustig theorem is now the following. You still have the theorem about the apex, that's no problem. Again, it works for any topstabler, which has Lustig basis. All of them, whatever kind of stuff you get. There's similar models for apex. But the H reduction only works for the odd, for D5, what's the odd case. The H reduction only works for the odd case, and not for the even case. So I can't write down the general H reduction statement. Here's a complex example. And it's really something silly that happens here. The only thing that happens here is that my H's, my SH, are not isomorphic anymore in any way. They're very different, and they even have a different classification. They're not even more returnable.
But I'm confused. So
Yeah.
when you say each reduction works, there aren't enough representations here.
They are. I will show you the example in a second.
I
I will show you the example in a second.
Yes, there are.
Sure.
Okay. Here's your example, Ben.
Are there two?
Oh, sorry, that's a question.
One-dimensional in the middle.
Oh, sorry.
row with the first three one. Like in there are like where's the missing one-dimensional one?
He's going to do it.
I'm going to do it. I'm going to do it. I'll be very explicit here. So character table on the left. There are 4 representations, as you probably miscounted. There are 4 two-dimensional ones, one-dimensional ones, the trivial and the sign representation, and the rotation representations. And you can rotate either by 60 degrees or by 120 degrees. And the count works out perfectly. 1 for the bottom, which is the sign representation, 1 for the top, which is the trivial representation, and the Z mod 2 gives you the 2 in the middle. Again, this works in general for the dihedral group. It's a bit more complicated. You don't get Z mod 2 in the middle. But it works. In this case, it gets as bad as you want. So I just did the calculation for you. It has characteristic, I did the same example, sorry. It's the same example, D5, but now in characteristic 5. And characteristic 2, you get 3 representations because 2 of them will collide. Yeah? Again, sign and trivial will collide. And that's exactly what you get. Here is still Z mod 2. Characteristic 3 works. It just gets a bit different in different characteristics.
Is this a good place to stop?
Let me just explain what fails in the other case by just making the same comparison, then we can stop. Okay, so this works. But if you do the same comparison for this case, so for D4, here we go. We have 5 representations of D4. Okay. Remember, you have 5. D4 is at the top. So no matter which one you choose as your SH, you undercount. You can't do anything. You really can't do anything. It falls apart. Bottom one, top one, if you want. You need 3 more. You don't get 3 more. All right, that's probably not a good place to stop.